Okay, so I think let us once again revise the diagram rules. Okay, so we were specifically talking about the Hugen-Holz diagrams. So the rule number 1, let me rewrite the rules a little bit more clearly. So we have each dot contributes to a matrix element of Hamiltonian, either one or two particle. So basically, two particle means two electron integral, and if it is two particle, then it is antisymmetrized. Okay. So for each of these, either F or V, there is a dot. V essentially is of course again two particle minus one particle. So one particle doesn't contribute, so basically two particle. Then the second is that all these dots have to be joined. So the question is that how many dots are there? So the perturbation order I can also write here that with one or two pairs of so each pair consists of one incoming and one outgoing line. So I have either one pair for one particle or two pair for two particle dots. And then energy diagrams are represented by closed diagrams involving this dot. So I just join all the dots in a manner that they are completely closed. Okay, then an imaginary line between the dots let me also specify right here that this matrix element is a numerator. So that these are constructed with sum over E of holes minus sum over E particles as the denominator, but the sum is the number of hole lines that this intersects the imaginary line that intersects, the number of particles that this intersects. Okay, is it clear? Then number 5 is, if you have in the entire closed diagram, if you have a number of holes is H, number of loops is L. Loops can very often be seen from the diagram or from the algebra. Then you attach a factor minus 1 to the power HL, H plus L. So, multiply by this factor. Then number 6 is 2 to the power minus k, where k is the number of equivalent pairs. So, what is an equivalent pair? It is either a pair of holes or a pair of particles starting from the same vertex and ending at the same vertex. So, starting from a vertex and ending at another vertex, which is basically have to be all same. And of course, at the end it is important to write that sum over all holes and particles. When you write the algebra, we have to ensure that all internal holes and particles are summed up. Okay, so we did some practice problem. So, one was the MP2 itself. So, we said this is MP2, sorry, this is MP2 in the Huygens holes, which is 1 by 4, this is A, this is B, P and Q, 1 by 4 P, Q, A, B. So, the matrix element that this contributes is basically the pair of incoming on one side and outgoing in the other side, or since they are all real, it does not matter, you can have outgoing here and incoming here. Okay. So, this is this. Then we did the third order diagrams. So, we saw there are 3 third order diagrams. So, these are 3 third order diagrams. One is a whole particle ladder, this is a whole ladder, this is a whole particle ladder. Okay. So, when you draw, of course, you can write the expressions. If I ask you to write the algebraic expression for this, I hope all of you can write it. Okay. So, just I am asking you a question, how many, what will be the factor 2 to the power minus, what is the factor here? 1 by 8. So, here also 1 by 8, here there is no factor, right, there is no equivalent line. So, just plus just 1, right, for the whole particle ladder, and then you have minus 1 to the power h plus whole. What will be the sign here? Number of loops. The number of loops is the only thing that you have to count properly. And when you write the numerator, actually from there also you can calculate the loops. As soon as you write the numerator, you can calculate the loops without looking at diagrams, whichever you are comfortable. So, how many loops are there? Depends on how you are calculating, depends on how you write the numerator. Let's try to write one of them, I think that is easier. So, let us write this A, yesterday I did not write the expression, right, A, B, P, Q, R, S, the first one I am writing, okay. So, these 4 are particle lines. We will put this loop rule little bit later. First, let me write down the numerator. So, this is sum over A, B, P, Q, R, S, 1 by 8. Then you have R, S. Now, it is a question of how you write it. RS antisymmetry is AB or RS antisymmetry is BA. You have two choices, right? But write it in some way, and accordingly loops will change. So RS antisymmetry is AB. So you have to now remember A is going to R from the diagram, and then you have RS antisymmetry is PQ, and PQ, just 1 minute, PQ antisymmetry is AB. You can write any way you want. Now you divide these two imaginary lines. Remember, when I wrote that rule, please modify an imaginary line between two vertices, between every pair of vertices, okay, in succession. And not every pair means not between 1 and 3. Every dots in succession, okay, every adjacent vertices, okay. So then you have epsilon A plus epsilon B minus epsilon R minus epsilon S divided by epsilon A plus epsilon B minus epsilon P minus epsilon P. Okay, fine. Up to this part, now we will count the loops. So let's start from somewhere. Let's say A. I have to come back to A to R, R to P, P to A. So one loop. Then I go from B to S, S to Q, Q to B. So I have two loops. See, A to R is R to A I can do. That is unimportant. That doesn't matter. So you can say A to P if you are saying A to P, P to R, R to A. So let me change it to ABRS. Because it doesn't matter, it is symmetric.
Is there a convention or you can keep it like that?
There is no convention as long as they are real orbitals anyway. Okay, it doesn't matter, they are identical. Okay. So we are all talking of real orbitals here. So there is. You have to keep track as long as the convention is same. So I think that will now cause your, so A to R, R to P, P to A. Okay. So it doesn't matter, you should not get confused by this. But so the point is here you have two loops. So the loops are very clear. That is, one is this loop. So if you look at diagram actually, one is this loop, goes here, comes back. So that's one loop. The second is the other loop, goes from here, goes here, comes back. So there are two distinct loops. So this is second one, I can label with the blue line. Okay. So exactly the same way I can do the whole. So this is the first loop. This, and comes back here. And the second loop is follow this blue line, come here and back here. So again there are two loops. Okay, and of course there are two whole lines. So this is the plus sign. Okay, and I can draw exactly the same way the whole, except the symbols will now change. I will have A, B, C, D and two particle lines. Let's try to, so we have another diagram, okay, so you can draw this. Let's try to write the third one. The third one, I can make three loops, okay, for the third one. For example, this can be a loop by itself. This can be a loop by itself, this can be a loop by itself. So there are three loops. Each of these vertices, you can have a pair of lines can be a loop. But again, it depends on how you want to write it. If you interchange, then loops can be two. Okay, I can interchange one line. But if I follow this, and that is the more ready convention, so A, B, C, P, Q, R. So let me label this again. So let's say this is R, this is A, no sorry, this is P, this is A, this is Q, this is B, this is R, this is C. That's easy. So I have three particle lines, three whole lines. So look at the first vertex, outgoing is C, A, okay, antisymmetrize, then R, P, then you have B, R, antisymmetrize Q, A. No, sorry. This is Q. The second one is B, R, then A, yeah, AC, sorry. Nothing. 1 minute. So B is going out, R is going out, and then A is going in, C is AC. Then the last one is A is going out, P is going out, no, not A, Q. Q is going out, P is going out, and then B comes in, A comes in. So you can see one loop is A to P, P to A, okay, and R to C, C to R, Q to B, B to Q, okay, the same way. This is Q, sorry. Okay, so that second one should be also Q. So I am drawing this diagram again here so that everybody can see. So the labeling that I have done is PA, outer line, this is P, this is A, then you have Q and B, so this is B, this is Q, this is R, this is C, okay. So that is the label we have done, and this algebra corresponds to this. So now you have to see the sign, how many internal holes are there, how many loops are there, okay. So how many loops are there? 3, the way I have written, and of course the internal hole lines are also 3, so it remains plus, and no 1/2 factor, there is no equivalent pair of lines, okay. So that becomes the algebra. So if I give you a diagram, perturbation diagram, you should be able to write the algebra using anti-symmetrized matrix array. Yeah, any problem? Huh? Oh, numerator, yeah, I'm sorry. I'm always forgetting the numerator. Yeah, numerator is easy. Of course, you just write it down. So you have epsilon A plus epsilon C, right? A and C, P and R. See, numerator you don't have to bother, there is no order or anything. Just see the lines, it's very easy. And then you have epsilon A plus epsilon B minus epsilon P minus epsilon Q. You just have to keep track of your symbols. Yes, total energy is sum. So MP3 is this plus this plus this. So that's why I've written plus plus plus. Okay. So up to third order, the diagrams, if you look at the third order diagram, they are also very similar to this diagram, and that is why they are called ladder diagrams, and there is no other possibility of writing any more lines. In fact, it can be seen that such diagrams actually come because of doubly excited determinants, that MP3 also contains only doubly excited determinant. I said that even in the first quantized, if you look at the third order energy, it is psi 0 0, V psi 0 k, then psi 0 k, sorry, psi 0 k, sorry, psi k 0, psi k 0, V psi L 0, psi L 0, V psi 0 0. Okay, so this is basically one of the major, and then of course you have a denominator. So here you can see that you have only Hartree-Fock to doubles, and of course this k must also be doubles because you have to come back to Hartree-Fock. So you have doubles to doubles and back to Hartree-Fock. So you have no other terms. Now you should be actually able to see the first quantized MP3 diagrams. They are not the algebraic expression you will realize that the actual expression is not so simple. The actual expression is a combination of two expressions, out of which a part of first expression cancels the second expression, and we have only these particular terms which in diagrammatic notations are basically just the unlinked diagram, the linked diagrams. And that was the basic idea of what we said is that the linked cluster expansion, that all parts of the diagram must be closed and linked. So if you refine that H1, all diagrams, one of the rules that we wrote, all diagrams are not only closed, all energy diagrams, but also they must be linked. So this is something that I thought I would not bother so much, but I can at least show algebraically where the problem comes from. So you can go back to the algebraic expression of perturbation theory, and we can write E03. So let us start from E03. I hope you remember how to write E03. Psi 00 V psi 02, correct? So if you remember E03 expression, it was psi 00 V psi 02, second order, right, in the intermediate normalization, second order. So we have to now get what is psi 02. So how do I get psi 02? I go back to my second order equation, H0 minus A00 psi 02 plus V minus E01 psi 01 minus E02 psi 00 equal to 0. What we need to do is to find out what are the expansion of psi 02 in terms of psi 0 case. Because remember, we will exactly like first order, we will write psi 02 as a linear combination of all k not equal to 0, which I now call ck2 psi 0k, right? The same expression that I use for the first order, except that the coefficients will now be called ck2. So I have to find out this ck2, right? I have to find out the ck2. So a specific Cn2 is nothing but psi 0n psi 02. So this is the matrix element that I have to find out. If I know this matrix element, then I know the entire expansion of psi 02. I will put it here and I will start to get E03, okay? So this is also psi n 0, okay? So let's now find out this, what is the value. So what do? I start with this expansion and project with a psi n 0, okay? So if I project with psi n 0, I will get En 0 minus A00. So I will get first En 0 minus E00 into psi n 0 psi 02. This is what I want to find out, remember. So that is what I get from the first expression, right? I am projecting with psi n 0 from the left. Then I have psi n 0 V. I want to write this as two terms, psi n 0 V psi 01 minus E01 psi n 0 psi 01, okay? This is not 0 because it's a first order. So this is the expansion that I get. So I write this as, this is bracket. So I have psi n 0 psi 02 equal to, I'll have two terms. One is psi n 0 V psi 01 minus E01 psi n 0 psi 01 divided by the denominator changed. Instead of changing sign here, I have just changed the denominator sign. Okay. Is it all right? So now you can see that when I put this back here, I actually have two terms. One coming from here, one coming from here. So if I explicitly write the E03, I will first get psi 0 0 V, and now I can expand this by putting an n here, okay, or this is basically the R resolvent kind of thing. So I can expand this by writing this as sum over n psi n 0 and then Cn 2, which is basically this term that I wrote. So this would be now psi n 0 V psi 0 1 minus E 0 1 psi n 0 psi 0 1 divided by okay, it looks big, but it's actually not big. What I have done here only because I have to write psi 0 2, I have written psi 0 2 as sum over n not equal to 0, psi n 0 and this coefficient. This coefficient is just here. So I have just put this whole thing here, including the denominator. So it's really not big. Okay. So just the denominator I have written here. And then you can see that I have two expressions. One is this, another is this. Each of the expressions have psi naught 1, okay, which I now know how to expand. And I will put that psi naught 1 expansion in each case. And then I will complete the algebra. So let's write the psi naught 1. So what is psi 0 1? This I already know. Right? So psi 0 1 is sum over some m. I am using a different dummy index from n. Sum over m, again Cm1, but now I know what is Cm1. So can somebody tell me again? Psi m 0, right? V psi 0 0, psi m 0, and I can write psi m 0 here. Divided by the denominator E 0 0 minus E m 0, correct? So all I have to do is in this expression of psi naught 1, I have to substitute that. So if you can see now there will be two double summation, and because psi 0 1 also has a denominator, there will be two denominators. Okay. So if you are just little bit careful with algebra, you should be able to write the entire expression now. So then your E03 becomes, let's do it carefully, sum over n, sum over m, both not equal to 0. Sometimes they just write prime here to indicate that 0 is excluded. You have psi 0 0, V psi n 0, that's the first term. Now I am multiplying this, psi n 0, V, and now I have to bring psi 0 1. Okay, so I do an expansion of m, and then I write psi m 0, close this. It has first the ket vector, so with which this will be closed, and then another factor will come, psi m 0, V psi 0 0, divided by E 0 0 minus E n 0, which is already there, and one more which is coming from here, E 0 0 minus E n 0. Right? So you have a double summation, but the story is not complete because I have a third term, I have a second term, which is E 01, which just comes out, which is E 01, which can come out, and then product of this with this, right? So E 01 times, again there is a summation. Remember, E 01 is a number, so I can simply take outside. E 01 is just a number, so I have a sum over n, sum over m, and then I have psi n 0, oh sorry, psi 0 0, V psi n 0, which is the first term, multiplied by this, into psi n 0, and now I write psi 0 1, which is psi m 0, psi m 0, V psi 0 0, divided by again these two denominators. Correct? So, it is very similar expression except that V is not here. It is directly psi n 0, psi 0 1. Yes. Yeah, we will come to that. Orthogonality. I am coming to that now. Okay. So, these are the two expressions. Now, you can see here that the expression becomes simplified for the second term because this is now delta n m. So, n must be equal to m. So, although there is a double summation, it actually becomes single summation. Remember, here it did not happen because there is a V. Otherwise, the expression is exactly identical. It is very easy to write. Take out the V from here. Okay? Instead of that, an E naught 1 has come. So, if you look at the dimension, it is same. You have 3 V here, 1, 2, 3, third order. Here you have 1 V and 2 V, but the third is this E naught 1. So, if you look at dimension in terms of perturbation order, it is still 3. Instead of V coming here, it has gone out. So, this is, of course, this can be taken out. So, n is now equal to m. So, I can put this as psi n 0, and the summation over m can be knocked out, and I can call this also E naught square, right? Okay, you write it. Now, it is very easy, just write it, just put n equal to m. Psi 0 0 V psi n 0, psi n 0 V psi 0. So, it is basically square of this, just like second order energy. But denominator is not second order, like a second order, denominator is a square. Otherwise, what is multiplied with E naught 1 looks like exactly E naught 2, except for this denominator. Otherwise, E naught 2 was exactly same, psi 0 0 V psi n 0 or psi k 0 back to psi 0 0. If you see this, psi 0 0 V psi n 0 back to psi 0 0, divide by the denominator, but now you have a square denominator, that is the only difference. Otherwise, I would have written as E naught 1 into E naught 2. It would have been even simplified, which is also dimensionally third order, but actually it is not, this remains.